Northwest University as part of the Multilingual Speech Technologies Research Group and also CARE. And he'll be presenting a paper titled Tracking Translation Invariance in CNNs. Christiaan, over to you.
Thanks, Koen. Okay, so if everyone can see the presentation and there are no issues, I am just going to jump right into this. So as Koen mentioned, today we're going to be talking about translation invariance in CNNs. This work was a collective effort by myself, Koen, who so kindly introduced me, and also our supervisor, Prof. Marelie Davel. So for a quick overview of what we're going to discuss today real quick, we're going to have a real quick introduction into the work that we're doing. We're going to really quickly talk about the related work, the optimization protocols and architectures we use. Then we're going to talk about how we quantify translation sensitivity, and then get into the bulk of our work where we talk about how we track translation invariance, and then also the effect of feature map size on translation invariance. And then we're going to have a quick conclusion at the end. So for a real quick introduction, now CNNs have become the go-to option for many computer vision tasks. And I feel most of us are quite aware of that. And it's widely believed that CNNs are able to learn translation invariant representations, but this aspect of CNNs is still very poorly understood. Now, unfortunately, due to their extreme popularity, several different architectural variations now exist, some of them much more complex than others, making them a lot more difficult to analyze and to dissect and interpret than they were a few years ago. Now, the goal of our research is to investigate how standard CNN components contribute to translation invariance. And we'll go over what we define as standard CNN components a little bit later. So really quickly, we're just going to skimp over some of the main points of our related work section. So Kay and et al. Have shown that CNNs can learn to abuse absolute spatial locations. And then Carl Lenk and Ava Daldy have shown that different CNN layers learn to identify different things depending on the depth of the network. Richard Zhang has also shown that anti-aliasing before subsampling does improve classification accuracy and generalization. And then one of the big themes of our work, or one of the big influences for our work, is work done by Coenraad Abrams, where they are able to quantify translation invariance in CNNs. Okay, so in our work, we mainly do our experiments on the MNIST dataset and the C410 dataset, both split into a train set, test set, and validation set. Now, all of the results that we show are averaged over three seeds, three initialization seeds for different networks on the same architecture. And then we strictly optimize only on validation accuracy. And then the standard CNN architecture that we use is a CNN containing three convolutional layers, each followed by a max pooling layer, then one hidden fully connected layer, and one output layer, and we use ReLU activations. So translation sensitivity quantification. Now, for a system to be fully translation invariant, the output must not be influenced by any translation of the input. Now, since complete translation invariance is near impossible with the CNNs that we currently use very regularly, we redefine the terms translation invariance to instead refer to a system sensitivity to translated inputs. Now, this means that a system can be more or less translation invariant based on the values we receive from the translation sensitivity quantification metrics, sorry. So these are those metrics that I just talked about. Now, to the left, we have translation sensitivity maps, and to the right, we have radial translation sensitivity functions. Now, this was introduced by Coenraad Abrams, as I previously mentioned. So let's quickly go over how we generate these. So to generate translation sensitivity maps, we take a sample, an untranslated sample, and we pass it to our CNN, and then we take the output vector of the final layer as our base output vector. We then take that same sample, translated by a few pixels, send it to our CNN as well, and take the output of that sample as our translated output. We then calculate the similarity between those two vectors, and that value is then represented by a single pixel on the sensitivity map. So every single pixel that you're seeing in front of you or on the sensitivity maps represents the network sensitivity to a specific shift. Now, it's important to note that we do this for every single sample in the test set, and we do for every single sample about 441 shifts, since we shift minus 10 pixels in the X to plus 10 pixels in the X and also in the Y axis. So These sensitivity maps give us a good idea of how sensitive a network is, but they are difficult to compare to one another. So what we then do is we calculate radial translation sensitivity functions from these sensitivity maps. Now, as you can see, all that we do is we calculate a radial average from the sensor moving outwards, and that's the function that you're seeing on the right-hand side, and that's what we use to compare our networks. Now, when we want to calculate the average radial sensitivity function for a network, we calculate that over all the samples in the test set over all of the classes. Okay, so let's start off. Now, CNNs mainly consist of convolutional layers, pooling layers, and fully connected layers. Now, it's important that this is what we define as the standard components of a standard CNN. Convolutional layers learn to identify features in an input. They then highlight and morph these features before passing them to the next layer as a feature map. Now, it's expected that convolutional layers should be able to compensate for most translation in the input, as they are more equipped to deal with translation since they move around the input instead of the fully connected layers just receiving static input. So these kernels are spatially aware, and like I previously said, they move over the input. So the first thing that we want to investigate is the effects of convolutional kernel size on translation invariance. Now, how we do this is we train 3 different networks with 3 different convolutional kernel sizes. Now, the size of the convolutional kernels are kept constant within the network over the network's 3 layers, but varied over the 3 different networks. Now, when you change convolutional kernel size, you have effects, or you see that your feature map size changes. Now, to ensure that the effects of feature map doesn't influence this experiment, we use zero padding to ensure that our feature maps have the same constant size across layers, across networks. And then in this experiment specifically, we measure translation invariance right after the convolutional layers and then right after the fully connected layers, so that we can see the effects that the convolutional layers and the fully connected layers have on translation invariance. And so these are the first set of results that we receive on the MNIST dataset. Now, to the left, you can see the sensitivities measured right after the convolutional layer, and to the right, you can see the sensitivities measured right after the fully connected layer. Now, interesting enough, you can see in the left example that smaller convolutional kernels tend to produce less sensitive feature maps. But if we take a look at the results on the right, this pattern definitely isn't there anymore. And the most interesting thing here is to see to what extent the fully connected layers actually influence translation invariance, which is funny because we would expect the convolutional layers to be able to deal with translation invariance fully. So as we said, the fully connected layers are responsible for a lot of translation invariance. And then these results lead us to believe that translation is still present even after going through all of the convolutional layers. Now, to further study this, we then decide to take a look at the feature maps produced by the final convolutional layer. So as you can see from this example, the top example is the base input and the feature maps of the 3 convolutional layers. And then the bottom example is a shifted input and the feature map produced of the 3 convolutional layers. And as you can see from these results, the shift is still present even through 3 convolutional layers. Now, we only show 3 feature maps here, but the pattern is present in the rest of them as well. So, since the experiments were performed on a very simple test, such as MNIST, maybe the convolutional layers just weren't forced to learn a better encoding scheme. So we think of 2 ways to test this. 1, we repeat our experiments on a more complex data set, such as CFAR10. And 2, we then reduce feature map size, limiting the space for movement within feature maps. So these are the results on CFAR10. Once again, to the left of the convolutional layer, to the right after the fully connected layer sensitivities. Now, as with the MNIST set, you can see that to the left, it seems that smaller kernels produce slightly less sensitive feature maps. And then after the fully connected layers, once again, this order is completely changed and all of the networks seem to have near identical translation invariance. So this is really interesting because we would have thought that on a difficult problem, the network would learn to compensate for translation a lot better than it has now. So now we want to change the effects of feature map size. So how we do this is that we use varying convolutional kernel sizes without zero padding. So as previously, we use the same convolutional kernel size within the network, and then we vary kernel sizes across the network. But like I said, we don't use zero padding so that the feature maps can change size. Now, to ensure that network capacity now doesn't affect our results, we keep the amount of effective nodes per layer constant across the three networks by adding channels to the layers. And these are the results. Now, since our feature map sizes are not constant, we can't directly compare C and N layer outputs, so we can only compare feature map, or we can only compare outputs after the fully connected layers. And as you can see, when we reduce the feature map size, it doesn't have much of an effect, except if we reduce feature map size to 1 pixel, completely eliminating the possibility for movement. We can see a high jump in translation invariance if we reduce feature map size to only 1 pixel. Now, unfortunately, in the MNIST or in the C14 results, the architectures weren't set up correctly so that we could see the one-by-one feature map. We just wanted to see the effects of the kernel size in this one. And as you can see, kernel size or feature map size doesn't seem to have much of an effect. But I did further study this in my distinction, and I can say that if we reduce feature map size in this specific experiment as well to 1 by 1 pixel on C14, you do see that jump in translation invariance that we see on the MNIST examples. So to quickly conclude, we focus on convolutional kernel size and find that smaller kernels tend to produce slightly less sensitive feature maps. We also find that fully connected layers are responsible for a surprisingly large portion of translation invariance in CNNs. And then we also find that feature map size doesn't seem to have a lot of influence on translation invariance, except if you decrease the feature map size to a single pixel, where you see a large boost in translation invariance. And thank you. That's it from me. Any questions? Sorry for rushing through it quite as quickly as I did.